Okay.
Okay, so let's get started. Today, actually, it's a very exciting topic and a great speaker. Um, Before we start, we'd like first of all, we start with the answer.
Alright, I'll keep it short. Thank you guys. My name is Scott. Thank you, Scout Cornelius, sponsoring this event. Just wanted to keep it short and simple. So first of all, we offer private banking, private business banking, and private wealth management. So we have some of our promotions over there as well as our suppliers. If you have any questions, you can talk to me. Personally, I'm really excited to hear this presentation, so I'll let you take it away now. Thank you.
So, I'm going to introduce Sandra Calico from Lynn. She's a founder, VP of Engineering, and Chief Data Scientist at Lynn. And she invented the Glint system, which is a system for extracting data from unstructured and semi-structured documents. And let her give more details on that. And it's based on an advanced machine learning approach, which has been widely published. Yeah. I talked to her about it, and it's very interesting. She's actually also deployed a number of production machine learning systems. She's actually doing advanced research in machine learning, and has been VP of engineering at a number of startups. And prior to that, in engineering management, taking and labs.
It's wonderful to see everybody here. I just want to get a read. How many people do AI every day in the audience? How many people are like, AI sounds really cool, but I don't know if it is, kind of. Okay, so I'm going to go 50-50. Okay, so my name is Sandra Carico. I'm the Vice President of Engineering and Chief Data Scientist at Glint. And what I'm going to go over today is architecture we use in the Glint system. And it's called mixed formal learning. And we published that last year and released it in a conference. I will go over an image example of mixed formal learning, and I'll go over an NLP example, which is really the Glint system. It's NLP. The mixed formal learning enables rapid, accurate learning from very low volumes of data. And that's why data is less remote, because you can take small amounts of data and, not quite amplify, but use it well. And I'm going to explain, using an example that Google published, how they used it well. Because they used effectively the same architecture. They didn't name it that for another case. I'll also give you our state-of-the-art extraction metrics so that you can kind of see how that works, and give you a preview for our next release. So I think when it's over, you're going to see how, to the extent that you can use mixed formal learning in your own applications, that data need no longer be a moat. That small, reasonable amounts of data under certain circumstances can be quite effective for learning, just as humans learn today. In addition, it provides interpretability for the AI models. Opaque models are gone in AI. So sorry, trying to get everybody leveled up here. So let's talk about Glint. So Glint basically takes forms like this and extracts them into JSON, so you can put them into Excel or databases. Turns forms to key value pairs. And it does it about 98% precision in these very small training sets, and it works across a variety of things. So why did we start this? What's the motivation for extracting data? Why? The reason is that data trapped in forms today is a source of tremendous drag on the productivity of the economy. It impacts accounting, where people have to hand enter data. It creates frictions in the supply chain, where they have to enter data by hand. It opens opportunities for fraud, because the data is trapped in form and it can't be audited well, so it gives opportunities for people to engage in fraud. Because data is trapped in healthcare records and doesn't move from system to system, it means unnecessary tests and other bad side effects can happen in healthcare. And then there was our case, which was it makes it hard to, if you have utility data, it makes it hard to estimate the solar installs, because you have all this data trapped in your utility bills and you don't have much energy that customer prospect. Most companies today pretty much resort to hand entering data. Or we can call that state of the art, let's call it typical. A step up from typical, people feel they're doing pretty well, they go into regexes, right? The regular expressions. And they create a system with varying levels of sophistication to look at the words in the document and then figure out, oh, that word means this, and that's where I put it in my database. Regexes work at small scale, but it's very time-consuming and expensive and brittle to maintain a large regex system. And for the engineers, these are basically scraping systems. And scraping systems are notorious. And it was where we were before we decided to approach the question of making regexes better. Because as we try to extract more and more data under more circumstances from more forms, it starts to become a challenge. We need a lot of programmers to chase it. And so scaling the company becomes challenging because, as we all know, programmers are really expensive, they're hard to find, and it would be much better if we could use different kinds of skills in order to solve problems in the company. But if we were going to do that, we were going to have to have very high accuracy, precision, is what we usually measure, and regular people would have to be able to train and extract data, train models and extract the data from them. And if something should go wrong, they need to be able to understand why it went wrong and correct anything that might happen. It had to be pretty transparent. Because we didn't want to hire, a Google-sized number of engineers. So what we ended up doing is creating an architecture that we now call mixed formal learning. Mixed formal learning has two basic components. The one has a formal model. And the formal model is basically some domain-specific math. You look at your problem, and we're going to see an example of this with Google. You look at your problem, you try to go, how can I think of this mathematically? What part of this problem, if I thought of it mathematically, could I do better? You're going to use some external data. You would probably see different loss functions than you might normally see. And you see that in the Google example. But at the end of the day, you're not going to solve your actual problem. What you're going to solve is you're going to pull out latent variables that are deep inside of it. And those are going to help when you mix those latent variables, probably with the same data or maybe some other data. And you put that data plus the latent variables, it becomes much easier to actually get the answers you're looking for. We're just going to give that traditional model a help by using this formal model. Okay. Are we all following? Good. All right, so here's our architectural diagram. So what we've got is there's some idea in our head of this formal mathematical model. Okay? And we're going to take that, and rather than specifying it like we would in the old days, we just straight up code, we're going to actually learn it. Okay? And we're going to learn it from some external data, perhaps, or some domain data. And that, once we learn this model with perhaps a specialized loss function, we're going to get latent variables that come out. There's going to be some variables that are predicted from that formal model. And somehow those variables are going to be helpful to us. And those combined with other domain data are going to make a series, one or several, regular plain old machine learning models. Now, I'm not going to specify exactly what technology you're going to use for those machine learning models, take your pick. The key thing is this idea of chasing after critical latent variables. That's
your initial formal model is trying to predict the whole task. Is that right? You're trying to create a mathematical model that does the whole task.
No, the initial one probably does not do the whole task. In fact, it probably only does a subset of the task. It may, in fact, only find some interesting information about that task. It just turns out that when you take those latent variables and combine them with the other data, it makes the next model's job easy. You're trying to figure out how to make it easy for the next guy. Okay? So we're going to look at an example here from Google. You can go to pretty good detail. It's published, and you can see the code. And in this case, and this I know I have run into these guys, women, over at NSC, and they were interested to begin with in the extraction of 3D key points. The key points are like consistent places on different views. So like if we took this can, we would be like, oh, the top of this can might be a key point. But we're not going to look at cans, we're going to look at, say, Ferraris. And we're going to look at a movie of Ferraris, like one after the other. When we have a movie of Ferraris, it's like a stereoscopic image, right? Because you have the first 2D image, the second 2D image. What we're going to do is we're going to try to learn a model from these two images that turns it into a 3D model, just like we do with our eyes. Okay? Now, the formal model is actually called the orthogonal proprieties problem. That was the math that they found. They went searching and they found the orthogonal proprieties problem. Okay? And the loss function is called the multi-view consistency loss function. What does that mean? It means you look at two pictures next to each other and you try to guess, given these two pictures with some offset, what might be the z, right? They have an x, y. What is the z for this Ferrari? And when you have the z for that Ferrari, what we have in memory is a 3D model or image of that Ferrari. Okay? And the way they did that was they learned a neural network and then got a 3D representation. So does this make sense? Two successive images. Now, we don't need just two, of course. We're going to take a small number, but we're going to learn it pretty fast, and it's going to be pretty easy to learn.
Question.
Yes?
What is the difference in your world between small and large?
We'll get to that in Glint. In their world, I didn't look at how many pieces of data, but it was also relatively small. They pretty much say this was easy.
Did they have the actual z values and the supervised training?
No, they do not. No, they derive it, and that's it. Because, so this is basic, so to my knowledge, they did not. So all they did is because they could look at, a long series of movies, and they could keep looking at different stereoscopic images, either the thing predicted or it didn't. And so from that, they would. Now, there are some, if you try this at home, be aware that when you put a camera on the front of your car and you drive it down the street, you're going to have some things having to do with the background moving. You're going to have to account for that and some other stuff. So there are some details if you try to use this for your self-driving car project. But the base of this is true. And they do have extensions now to this work that deal with those questions when you put it on a car and it's moving. But this still works. Okay, so now we're going to go after these key points, because the first thing we did was something weird, right? We took two images, we turned them into a 3D representation in memory of a car. And now we're trying to find some dots. Now, key points is kind of a off in the weeds kind of topic, but it's a thing people do. They want to find these spots on objects that kind of stay still. And typically, these things are supervised. This is a supervised job. Somebody sits there and marks dots on images. It's difficult. It's painful. It's not a job I don't think anybody really wants to do it. So, and they didn't want to do it either. So they used self-supervision to figure out the key points so they didn't have to mark the darn things. And the way they were able to do that is, once again, there was a loss function. Now, again, a very popular loss function in this kind of world is called a differentiable relative pose estimation loss function. And they use a neural network again. And from that, so you can imagine in memory, we have this 3D image of our Ferrari, and we can see it moving through space. Maybe we can find spots that stay the same as we're moving through space. And that's how we start to find these latent variables. Okay? So that's really what we're doing. And then we got some answers. And they did a really good job with it. It works great. Now, in and of itself, you might go, well, who needs key points? I mean, yeah, right? In 3D models. Well, let's just take this as a hypothetical, going forward, and imagine some reasons we might want to do that, right, in our self-driving car project. Well, imagine that we're able to consistently get these hypothetical key points that I crudely placed on these images. Well, you could imagine if those were consistent across cars and consistent across bicycles, that you could start to classify based on key points. What was a car? What was a bicycle? What was a human? And with some other work, you might be able to ask questions like, how fast is that car moving? How fast is that bicycle moving? Where is that human going? And now we can say, well, I'm a car, I'm going this way. There's a human. I classified it by its key points because I noticed a pattern. Bicycle, I noticed a pattern. And I said, that's a bicycle. And now I can ask the question, well, I hit it. So let's try to wrap that up and make some sense out of what's happening. What's really going on is that by creating this library of capability where we can understand the domain in pieces, the key points, you've got the 3D model, all of these different parts come to bear on the problem domain. Cars and self-driving cars are rich problem space. We need a lot of information around that. So these clues combine and form sophisticated behavior. And you can start to build up capability across the domain with these latent variables to help learn stuff. And that's kind of why I did this puzzle piece. You've got this eye, this other eye. These things start to come together and form a whole. They make a cohesive whole. Now, of course, what does this mean if you're doing this? You're playing this game at home. It means you do have to understand your problem space pretty well. And you have to listen. But it really helps to learn fast. So let's look at some of the results of that where we used it. Of course, we didn't use the orthogonal Prokruski's problem to extract data from forms. We did it differently. But I think the and this is a preview of actual data from our next release. And I don't know, can you guys read the subtitles or should I narrate? You're good. So this data is actual data from the next release of the machine learning. So this is actual lab data from my computer. Then the UI is indicative. It's our UI where I had to back it in because it's not integrated yet. But you can kind of see with 3 documents. You can see 3 documents at the top on a clean system. Training single shot, absolutely clean. The extraction going across 2 other documents. And obviously we use the UI to demonstrate that visually. Some of the CADing files. And so the ability to basically go from a de novo system to single shot is huge, right? Now, we're not going to ship just single shot. We'll have low shot and so on. But I think the capability on that is pretty impressive. One of these cool. And so you'll see it still misses, right? In this case, we found everything, but we missed the specimen type. So, that's going to have to get filled in, sent back to the system for more training. The single shot doesn't do it all. And then it can do better on the next try. And then I think I go through each one of them, and you can see that all fields are found except for that one. Now, the other thing it does is, so you can't just have one capability, right? Because as we saw with the Google example, once you start to develop these libraries, you get more capability, and one of them is classification. There we go. So the system's able to do a very good job of classifying, and so we can start piling on different classes of forms, training each one with a few at a time in order to extract the data. And obviously, you have to have training for each form type because it's not a general form reader without supervision. It needs a little bit of information. Let's talk about why we need some supervision at all, right? And the reason we need some supervision at all is because in practice, when people use this, they want to name their fields, right? They don't want you just spitting out, numbers for 32-gallon trash. They want the words 32-gallon trash exactly written this way with exactly that number next to it, because otherwise they can't put it in the database. So the problem space without at least a single shot doesn't make sense to the user because they don't know how to use. Otherwise, you get the jumble that's OCR. Okay? So we wanted to synthesize and organize that jumble. You can see on this one, it's single shot. I think it's 32-gallon trash.
So could you take an OCR off the shelf and use that as a mathematical model?
The OCR is, we don't provide an OCR. We use any other third party's OCR. And from that, then we start our work. That's what we start.
So you need a large corpus of unclassified documents combined with mathematical model of the existing OCR.
So in practice, not more than 20. 25 class. Correct. So yeah, there is some self-supervision, right? So you label one and it starts looking through and sorting
So
it out.
I'm missing the piece how you go from the mathematical model to the large version of the variables.
So the mathematical model is basically has like a car, right? It extracts some important latent variables that the next model can work on and choose. And then it makes it easier to back out. But that's all kind of it, and that's our idea. That's the
I was imagining what you were saying that you took your mathematical model and you have like a large corpus of unclassified stuff and help you sort of classify and try to replicate that with the network or something. Like you would then pull the variables out. But that's wrong.
Yeah, no, it's a small corpus. It's a small. Everything is small. Because when we had a problem space, we don't have a lot of data. These utilities are fractured. There's like, I don't know, 2,000 or 3,000 utilities in America. Mark probably knows exactly how many. And we're not going to get 100,000 from PG and 100,000 from SCE. We're going to get like a handful. So we can't need 100,000 to survive.
So this could be characterized as human in one way. So you basically
semi-supervised.
Semi-supervised, but effectively every example is going to be classified or extracted, and if it's a yes, no, change this.
That's right. At least once.
How much advantage do you get from using these attributes that you're creating compared to running without those attributes, still having a human in the loop?
I'm not sure I understand. So we need the human in the loop because we could get all of the things from OCR, but we wouldn't know what you want to call.
Okay, but if you just have human in the loop,
Yeah,
rather than and not your special secret source,
sure.
presumably you get this eventually.
Yeah.
Can you characterize what reduction in the number of documents a human needs to look at you achieve through using this technique?
So I guess I'm still a little unclear, but what I can say is that using this technique, we're going from, well, I mean, we're able to, let me show you a graph. Let's see if that works. Let me show you a graph, and it may, let's see what we get. Maybe this is kind of what you're looking at. So our training sets are, yes, I will. So this says STB accuracy. That's really, it's precision. Okay. Since I think we took this from marketing, so that's a precision. Our y-axis are precision, and the things along the bottom are number of documents in training sets. And for those of you who can't read, that's like 1 to 10. Okay. And that's what we're converting. And then if we look at a neural network, we have thousands here, and we're converging very fast.
So sorry, I get, but one is there's other systems out there. So there's long history systems where you have document after document. So written down rules back in the 90s and such like.
Okay.
So can you compare to those sorts of? You're comparing to batch learning.
Yeah.
What about other systems that also are looking at document by document, similar sorts of numbers?
Yes. So
So you're probably getting. I'm assuming you get an increase in power, maybe a 10x increase in power or something like that.
oh, probably somewhere between at least a 10, maybe 100. The biggest problem with those old systems is they're brittle. They're using effectively regexes. Even if they're not regexes, they got rules, but the rules break.
Oh yeah.
The rules break.
Absolutely.
And so every time that rule breaks, you have to chase it down and fix it. And with this system, and then you have to reboot it. So, you're looking at, and the reason we did this was because we were doing something like this. I mean, obviously it wasn't just regex, but
But it certainly makes sense. So you're building these meta attributes, which are creating that sort of generalization power.
exactly. So in practice, it's a huge difference. And our accuracy is much better. It's precision, really. So we've looked at other systems that do this, and ours, and so it's a big difference. And I mean, it doesn't sound like a lot, right? Because you might be going from 91, 92, 93 to 98 and a half, 99, which is where we're at. But that, on big numbers, it matters.
For the types of documents that you're training a small number of, are they the same type of document with different input data, or are they slightly different documents?
We can take whatever in that space. So if you see, so we take what? The way I like to explain it is, give me documents together that you would, in all honesty, consider the same. So, you have a PG&E bill that comes to your house. Of course, the line items move around. There's a Christmas message on top. But as far as you're concerned, it's still your PG&E bill. And we are resilient against most reasonable changes. And we're getting more resilient every day. But we are pretty resilient. So let's look at some examples with small training sets. Here's a study with 4 different sets. So you can see how it works across, and I think because of some confidentiality, we couldn't really specify what those sets were. But we tried to make it fair, right? Some of them start out really bad, like set D at 50%. Some of them start out pretty good at 95. And I think that's an F1 score. I think that this is Y is an F1 score. But you can see pretty much by 8 or 9, we've converged. And then I'm just going to go through this for people who are like, what's your measure? How do you measure these things? So a field is right or wrong, full stop, right? If there's a single character wrong in a field, it's wrong. That's it. We don't count the number of characters we got right across everything and then divide, because that would be kind of crazy. But some people do that. So our granularity is a field. We use an F1. Our F1 generally is about 95%. Just to review, that's a harmonic average. That is our formula. Harmonic average. Precision, which I've talked a lot about today, is the number of relevant documents combined with the retrieved documents divided by the retrieved documents. And then recall is the relevant documents and with the retrieved documents divided by the relevant documents. We're pretty consistent. On precision, 98, 98.5, somewhere in there. And then recall is, that's fun with selection bias. So we've tried a number of things to try to figure out what an appropriate recall is. And it's somewhere between 80 and 95%, depending on how you do that. Because you can get anything you want depending on what selection, what you selected for the group. But of course, we don't care about necessarily how the Win system performed or how this unusual system with Google performed. What we want to know is how can we play this game at home? And where can we find methods to do this for our own projects? So my suggestion is if this seems like an interesting way to solve your problems, I would be looking at operations research. Because operations research, basically the whole game there is find piles and piles of math and figure out how to apply that math to some real world problem and then make a prediction. The trouble is the way they do it today is when they do that today, they just try to do a closed solution. They don't actually learn the answer. If we start applying machine learning to those things, as Google demonstrated, I think we can do much better. And we can use it to extract latent variables and then use those to feed our models. And the reason we're doing this is we're trying to model what is our problem, whatever that one is, any of you should have. And we want to figure out, given that model of our reality, whatever your reality has to be, how can we pull out some variables and give that next model or the next series of models a fighting chance of getting it right. People are curious. The next formal learning paper is on archive. Like 3D sequence. It's on archive. This does read a little bit on the BERT system. You can read that. And then I have Forbes articles that are a little bit more accessible. Data is really a moat. We just kind of put this in. And then your successful AI project will probably take you 15 times more work than you think, which isn't bad. And make or buy. And I know there's a question in the back. Yeah.
Yeah, so I'm wondering what types of models you find work best for you. Are they simply mathematical models that are kind of pure ML types, or are they more ML types?
In practice, well, first we don't specify what models we use internally for obvious reasons. But in practice, the ability to find key data is the key. If you can find really, really good data that's highly predictive, it's really, really helpful.
Can I ask a question?
Sure.
Can you dive a little bit into data is not
Sure.
Not it's very hard to hear.
Oh, okay. So I'm just asking Sandra to give her take on data is not a known type.
Yeah. Yeah. So so why is data not a mode for this? How does that relate? It relates because when we start to learn these formal models, things converge fast. Your machine learning will converge so fast on so little data, and even if it overfits, because you're modeling the actual problem domain, even if it overfits, you will probably be fine. Those latent variables will probably still be extremely helpful. And so what happens is that math just accelerates everything. It requires so little data to get a decent machine learning model that you don't need much. Right? Google didn't need much. We don't need much. We showed you that. And then when your latent variables and your other variables come in and you go to the next model, you're so close that it learns fast too. So we have at least 2 proof points of that. And I think there's actually some other examples inside of Google where they're doing that as well, with good results.
So studying this space for quite some time, I've come across problems in statistics with IIP data. So if it's identical and it's independent and identically distributed.
Correct.
That's the problem because you're removing dependency from the data itself, even though it has some. So you're not end up modeling the real world.
That would be bad, right?
Right. That happens every day.
That's right. So what we're doing here is we're actually really pushing to getting very, very orthogonal data that is very helpful for finding things. So this actually, in effect, is trying to get very diverse data, small amounts of it, leveraging it, and finding the key important pieces. I don't know if that helps.
Right. So then, are you not using algorithms that are, say, feed-forward based that require IID data?
Well, I mean, I believe that if you look at the total cases, it's equal.
Okay. Those algorithms require IID data or have this data in IID form in some way. That's fine. And the other question is, if you represent the data in a more non-independent form, right, that will try to stitch back together the independent stuff. But,
I don't know, I have to look at it, for sure. But I think the important thing is what I'm really trying to do is I'm trying to stitch together the data I'm trying to find interesting, what I'm trying to do, well, this is the way I like to think of it, like more layman, which you are not, because we talked about there. But I have, what I'm trying to do is not throw out data. Very often we have a lot of data in our data sets that we ignore. For example, in a movie, we know it's sequential. We know that can be stereoscopic. We throw it out. Don't do that.
Agreed.
So I think that that's really one of the key contributions. It's don't throw out data you've got, because some of that data is deeply useful. And if you know that you have it and it's kind of buried, like in the case of the two Ferraris, learn it, pull it together, and use it in the next step. I think that's really the message. Yes.
Just to go back to some data is not about. So it seems like the current training AI is, you have to no feature engineering.
That's right.
Right. So which is kind of, I think it's a way to democratize a lot of the work also. You don't need to be an LP expert. After all, the parse tree is structure.
That's right.
And I think that's what powers up the current training AI is that you can be just a machine learning person. If you know anything about language and semantics and syntax, don't know anything about like 3D rendering of objects and mathematical models, you can just do the thing and at least get some value. So now it seems my question is this kind of approach is very variable, but don't also be like backtracking in a sense, and now we are okay, that is not a mode anymore, but now expertise is back to being the mode. Because sure, I can tell you are using character-based encoding of your text. Believe me, I'm doing MPI. That you're missing out on some data here. But now, do you need to learn, 30 years of syntax and things like this, or no? I mean, then there is another mode, which is the knowledge of the domain.
That's right.
And for me, I just think this is an interesting balancing act, right?
Yes.
Because to be able to do that, I like the fact that people can approach things into machine learning algorithms. But now we are back to other ones. So is there a way out of both?
I'm not sure if we can get out of both. I mean, it's certainly true that when I look at this, I go, wow, aren't we back to feature engineering and thinking hard about problems, and the smartest programmer wins? And versus, basically the current thing where we take a giant sledgehammer and we do what I call electron genocide, and we just beat the crud out of it. It's a trade-off. The current system requires so much compute. It can be overwhelming and inaccessible. I mean, I know I talk to people that look at, like this new StarCraft. Did you see the StarCraft solution? And people are like, oh, I'm not going to use that. It was like, what, 7 years of compute on like 100,000? It was crazy. It was inaccessible to a normal person because, you needed basically a nuclear power plant next to your data center.
So I'm still trying to understand the model and the requirements. Okay, for example, in my line of work, I had lots of mathematical models sitting around people,
Fantastic.
and I mean, very complex ones. Some involve solving optimization problems. Sure. They go to all sorts of problems. So, I mean, does that serve, all of those serve the purpose? Does the black box mathematical models serve a purpose? It doesn't have to, is that your algorithm look inside?
You don't have to look inside of it. So all that really matters is that you can get out of that map, right? You can get some variables out that are helpful for the next model, however many nexts you might have. And if you've got those things laying around the house, use them.
So these models, I feel, are very structural. They tend to do things like this. So they're hand-built. So I'm wondering if this is, so obviously they have variables all through there. They're there for the reading. But like said things aren't really independent. Their models is independent. Things like that, right? So the neural network could potentially get a higher fidelity representation, right, of these models because they might get some of that fuzziness in it. So that would be perfect. It would be, you take these variables as people see them, and then the network take it to the level.
Exactly. And this isn't like, and none of the, in effect, if we want to think about retreading, right, that's a lot like what we did with autoencoders when we first started down this path, 10 years ago, right? What were we doing? We were taking in data, we're compressing the crud out of it, and we were getting out these features. And we're taking those features, we're putting them back on the front end of another. And we're doing that today with the multi-world thing, the big paper. They did a variational autoencoder. They crushed it down, they pushed it back, and moved it through another neural network. Because in the crushing and in the compression, we have great features. So use them. Just because the fashion is to, kill electrons, don't be a slave.
This idea of fast learning, yeah, it's a key to solve a problem.
Yeah.
Reinforcement learning stuff is, this is a big thing that all researchers are talking about is, these massive successes stuff, DOTA and all stuff.
Yeah.
But it's a, what is it, like 2 million hours to play to get to that level. And, then people usually want to dabble and they learn how to do it.
Exactly.
And that's a big of a solved problem. So, I mean, this is, any way to get there is look twice at it.
That's right. I mean, if you look at the Lin system, it's basically learning at the rate of a small child, right? It's like you sit them down, you say, here's a form. Okay, I want you to find this field. Great. What do you want to call it? I'm going to call it this. Then they go through and they keep extracting it, and then they're like, oh man, you told me this is the same form, but it's here twice. I don't know what to do. How do I look at this and say, do it this way? Okay, I'm not sure. What about this one? Is it the same? Yeah. Okay, I got it. Until the next confusion, right? And then like a new form comes up they've never seen. They're like, great on those PG&Es. You told me about them, but what's with this Office Max? I don't know what to do with that. What do you want to call those? What a piece of data you need? Oh, okay, I get it now, right?
So now you put BERT on your recommend readings. You obviously see a connection.
There is, yeah. I mean, certainly, yeah. So certainly, if you look at the key points stuff, that's very attention-esque, right? There's some stuff inside of our stuff that starts to really start to look like attention. So I think that the BERT work and the transformers and the attention actually start to read on this because they're kind of doing the same thing. They're trying to push things down into a transformer in order to pull out the important things. It's not 100%, but it's more related than it looks. And so I think understanding the BERT work and the subsequent work that came after that is probably valuable because in the general, like as a pedagogical exercise,
The Excel next.
yeah, because that's, I think it's related. I think there's benefit to that space.
Yes.
Yes.
Yes. Yeah.
Can you speak up, please?
I'll repeat it.
Okay. Yeah, so I have some problems with my data set because my 5 years ago I established a team to sort of the data to label data every year it changes, every year changes. And I put all of the data into your format.
Yeah.
Probably it would be easier to extend this or just summarize knowledge. But I want to do some prediction or to find some correlation to every year's
Okay, so I think the question is a product question, not a theoretical question. And what she wants to say is that she has a lot of data in forms, and you carefully labeled for 5 years pile of form data. But the forms, as we discussed, they drift. And she's like, well, how do I manage this drift? And can this system manage that drift over time? And the answer, and what does the product do with respect to drift? And I think the answer to that is it depends, right? It tries to be pretty resilient. And my general measure for rule of thumb is if you showed that drift to a child, a 7 to 9 year old, and you said, can you understand what to do with that drift? It will probably work. It will probably go total amount due here is total amount due here, just as a basic rule of thumb. If, however, you gave those 2 documents to a child who is extracting them, and the child would go like, tell me what to do with this because I got no idea. You got total amount. It's crazy. It probably won't be able to figure it out. But what it can do is train fast enough so that as that drift occurs, you can start extracting it and calling it the same thing over and over again. And so there, it would be more like it's a different document or a different variety, different presentation. And we do presentations all day long. Because if you look, obviously we do invoices, but if you want a really complicated invoice, you look at an utility bill. Okay? They are crazy people there. All kinds of things all over the place, and they have presentations that change. It's nutty. So we're pretty good as things change. Yeah.
In your description of these things, you mentioned that there's a lot of feedback given to the system. Do you have an example or maybe how the interface, how that works?
So the system itself does have some exposed variables inside for internal trainers to understand where things went wrong. But over time, we expect that there'll be less and less inspection. So we don't expose that because it exposes our IP.
Okay, so most of the training is done in-house, and then
Actually, we're exposing training to the outside world, and within the new version, you will even today do your own training.
okay, I see. So then feedback is still with the user then.
That's right.
Okay. So can you explain a little bit more about that interface to the user? What does that look like?
That was what you saw. That was that. I can go back to the movie, but that is pretty much the interface today. I just took my next version and I showed the integration with doing single shot. So the way it works is pretty much that UI. It's just it doesn't automatically predict in the background. It's like you label a bunch of stuff, go, I'm done, train, and go. So we don't have that fast loop. That's what the next version is.
Okay, so it's still visual. You see the document. You point out the area field.
Correct.
And you have the rest.
That's right. Yeah. So that is our current UI, and the only thing is, it's like a batch train, right? So you go through, you label all your documents, then you say train. So you have to hit the train button. That's the way it works today. In the future, you'll get this kind of integrated, dynamic experience. That's the difference between the current system and the next system. It's kind of slicker. You don't have that dynamic experience, but you're You're not labeling that many pieces of data.
A little more interactive, a little less blank.
That's right. But it's still about 10 documents.
Fair enough.
You have a question? You have a question? More questions? Let me ask you.
Sure.
So this is more data always comes better. Then along comes Martin Casado. He writes, data is not enough. Along comes Simon questions, data is not enough. Get confused.
Right.
What is it?
So,
Because Anand also has real examples of stuff where just adding more data, using
it helps. That's right. It's a question of where you want to make those trade-offs, right? Just because you can apply 100,000 or 200,000 pieces of data to a problem and get the answer, and basically, use it for your power plant. Great. But you don't have to. If you want to use a little bit more ingenuity, you can get around that. And a moat to me means if you don't have all that data, you're out of luck. If you're not Google collecting this giant stream of data coming at you, you can't participate in this revolution. And I'm here to say you can participate in this revolution, even if you don't have petabytes of data coming from their site.
More questions? Oh. How about we're talking about some of your experiences? Getting input from an expert. Any good experience? I'm sure all of you have good experiences. You have to talk about it. Was data an advantage? Give you a first mover advantage, but not something sustainable? Or did it actually give you a moat that is uncrossed chasm?
We have to say every example I encounter, they always have far too much. They always have high expectations, have very little data to do stuff with. Definitely, yeah, so, and that seems just ridiculous. People nowadays have this huge expectation of what's possible. So, I mean, I do think, like for anything like this, if you are doing that language and stuff, or and transfer images are great resources. Those are examples, where you kind of can do some stuff at reasonable scale, but yeah, kind of close to the domain. So we have, like, I work in an area where we have people with, like, I'll give you some examples. We have models where people are trying to figure out where to put the power plants on the electric. Okay, or where to put batteries on the electric. And there's, basically you're looking at what might happen in the future, simulating the grid, the traffic on there, and you're trying to figure out, using optimization stuff, how the power is going to be dispatched, and from that, what the value of these batteries are. And this computation to figure out how power is going to be dispatched and stuff involves optimizations and all sorts of stuff. It's very time consuming, and it makes it hard. Then we like to run Monte Carlo simulations on that to assess uncertainty. So if we could train a neural network that would sort of automatically predict dispatch, or do a generative model or something, predict dispatch, and then we sort of Monte Carlo simulate, reduce the more fast model, and that would be great. But we look at that, it's like, well, I'm not going to get 100 data points to run these solutions, because it takes 24 hours to solve, and stuff. So, so I'm listening to this kind of wondering, is that nonlinear optimization sufficient mathematical model that would enable, enable this kind of learning a problem like this?
I mean, I would suspect it would. I mean, if you take a look at, the kinds of data sets I'm using, I'm learning to know off like single documents, right? We have a couple, but that's not a lot of data. Google was doing their neural net. I don't know how much they used, but they were like, did not take much data, convergence fast. In fact, these things converge so fast, people go, oh, you're overfitting. But if you're overfitting an actual thing, no, you're not overfitting, you're solving it. At some point, you cross the line from overfitting to solution. So I would suspect it would probably yield. It's just that everybody's so used to an OR doing those kinds of things. They're like, okay, this is the way I do it, this is the way I do that, this, you know. And I've talked to OR people, and I'm like, and you know, these are like the leaders in the industry, right? Who get hired by, you know, the best and brightest in America. And I'm like, have you thought about putting some machine learning back? And they look at me like, huh.
Yeah. Although I have to say, the last 6 months, I went to every single talk.
So good. They're kind of,
So that was permeated the OR community, but
yeah, but I mean, just a year or two ago, it wasn't. I was just going, oh my gosh, it's wide open.
yeah,
The space is wide open.
yeah.
They're open back to defining deep learning. Deep learning is a small part of the space. That's scary. Right? You see everyone going headlong down that particular route.
Yeah.
There's so many other options.
Yeah.
It is, I agree. Yeah.
Yeah, I mean, you can do any kind of machine learning.
Well, so another one that you can is that natural language is a great application for doing small numbers of documents. Kennedy, I was at CGS every while. He used to do it, and we take a bunch of docs and ask questions of it. A small amount of cheating, a very similar way to this, to say, you know, that was almost right, but I need the other answers. And it rolls back in.
Right.
So there's a rising tide of these sorts of single shot, well, 10 shot.
Right. Low shot.
Yeah, low numbers of shots, solutions out, which is fantastic.
Yeah.
What's something you're thinking of just, what's your experience doing sequential kinds of specific documents?
So some time ago, around 2000, I was involved with a South Australia that was doing book-down rules for pathologists.
Oh, sure, that's the way they used to always do that, right?
Yeah, this was, and came out of that recognition that the expert system just didn't work.
That's right.
Right, the world is not platonic, and so the book-down rules were created, you just go and create an infinite decision tree. And we had various ways of reducing the complexity there, so you could create intermediate variables and things like that. So you get a little bit of generality, but we're seeing more and more of that come back. A lot of people who are involved with the recurrence of symbolic, if you like, in the moment, have then coming back and saying, let's have this human loop learning work much more effectively.
Right.
Now, I'm not convinced it'll work for your problem. I think you need to work. I'm serious.
Yeah, so I think these rule down rules, so I'm starting to get my head around the questions you were asking earlier. My experience with those kinds of rules in the expert systems is they're very hard to develop, and they're very hard to maintain.
This was at the very beginning of machine learning. It's an interesting crossover.
Yeah, so that would be why I would avoid those. Okay.
Well, there's multiple versions.
Okay. Okay, but yeah. For those reasons, I would have give me pause.
Types of operations research methods that
I think in my paper I listed some, and they're not coming to my mind right off the top. There's things with.
What was the question?
What kinds of OR formulas would you look at? You know, can you make that more real for me? So in OR, there was there's a set of formulas, and I don't remember the names of them, but basically they have to do with the filling of dams, right? How do you fill and release water from dams? And they model it in a certain way. It turns out the filling and releasing water for dams can be used in things like managing warehouses. You could look at a warehouse and the income becoming inventory as, water coming into the system, and it fills up a reservoir, and then they come down, and then we're going to model it as a dam, as a reservoir of water. So that would be an example where they're taking very particular models, and I can't remember what map they use, but yeah, that's another white cube. I think they were using like finite elements is coming into my head. I don't know if that was what we did. But you can see certain types of these. I think we look at the work by Stephen Green at MIT. You'll see some examples of how he's applying different kinds of typical applied math formulas. This is the world of applied math, right? And so you're going to be looking at things like the heat transfer equations, right? You're going to be looking at fluxes, those sorts of things. And then they take that and they say, well, this is just like, flux around the fuel rod. This is just like a heat transfer thing. What we're doing is we have heat here, we're transferring it over here. And it's a good model. It's fake.
That's my co-founder, Dan Turchin. So we're coming up with the pitching now. So I have one last question.
Sure.
So Glint AI is offered up as an API that does.
That's correct. Yes.
So the possibilities for entrepreneurs here is to build their own business process flows on top of this. Can you go into it a little bit?
Sure. So ways you can use. So if you so this would apply I think more for you and fun.
Or for any entrepreneurs thinking of specific business model.
Right. So the extracting data from forms is a deceptively hard problem. People think it's easy, and kids say I can get it done, and it is stupid hard. So don't go about solving that. Just use our API. I had a woman call me this morning, and she said she's working with the schools in California with special education, and the parents can have hundreds of different types of forms where they need to track the progress of their children. And so she needed an application to try to get that information for the parents to have it in a single place, and she was going to turn it around, and she was going to give it to have the state have it so that they could get that data. And now you're going up that stack, right? Going up the stack, and you're saying, what kinds of problems can I solve? Say you're doing some kind of supply chain thing, right? And you're trying to get a better solution in terms of ordering faster. Well, if you can get stuff in the manifest, get that out fast with a scanner and the dock, how much better can your systems work if you're going all the way to the dock with a scanner, uploading it off your phone? So the capability of being able to reliably know you can get data out of the form wherever you happen to be, whether it be in healthcare, supply chain, dealing with children, dealing with inventory, it's valuable.
And a lot of possibilities in terms of building interesting business process apps on top of it.
So I work with Sandra, and I'm compelled to say our UI requires no coding. You can upload documents, get data extracted, and back to you as a spreadsheet. For anybody who doesn't code but still wants to get data out of documents.
Thank you. Thank you so much.